So hello everyone, welcome to this lecture. So till now in previous lecture, we have seen how to represent a complex number into different forms, right? So first this lecture will start with one question. So in this question, they gave a complex number z r. This complex number is equals to cos pi upon 2r plus I sine pi upon 2r. Find this continued sum r is equals to 1 to infinity z of r. What does this symbol means? This symbol is a symbol of continued product. Continued product means here there will be multiplication operation between two terms. So when you will expand this one, zr, keep r value as 1, we get the first term. Keep r value as 2, we get the second term. Keep r value as 3, we get the third term. And so on, we have to go till infinity. And between two terms, there is multiplication of operation. We have to multiply all the terms till infinity. Got it? Now, first we'll see this complex number. This complex number zr, they have given as cos pi upon 2 the power r plus iota sine pi upon 2 the power r. So we have seen the complex number representation in Euler's form, right? So if I'll write this in Euler's form, I'll get it. See, the magnitude is 1, right? Because what is the magnitude? Magnitude means under root of real part square and imaginary part square. We'll add. So cos square theta plus sine square theta is 1. So here the magnitude is 1. So our value is 1, and then we can write this as e to the power I pi upon 2 to the power r. This is my complex number zeta. Now we'll keep this to calculate the product till infinity. So r value first we keep 1. So we'll get e to the power iota pi by 2 multiplied by, next will be e to the power iota pi by 4, right, to power 2, multiplied by, next term will be e to the power I pi by 2 cube, multiplied by e to the power I pi by 2 to the power 4, multiplied by e to the power I pi by 2 to the power 5, and so on till infinity we have to add. Now base is same, so I can add the powers. So this one I can write as e to the power I pi by 2 plus I pi by 2 square plus I pi by 2 cube plus I pi by 2 power 4, and so on till infinity. So this is a sum of infinite GP, right? So first I'll take iota pi common. If I take iota pi common, here I'll get e to the power iota pi I will take common. So here I'll get 1 by 2 plus 1 by 2 square plus 1 by 2 cube, and so on till infinity. What is the first term? First term here is 1 by 2, and the common difference is also 1 by 2. So we'll apply the formula of infinite GP. The sum of infinite terms is a GP. So this will be e to the power iota pi, and the sum for this one will be a by r minus 1. Sorry, 1 minus r. A by 1 minus r. Got it? So this will be e to the power half by 1 minus half is half, only half by half is 1. So we'll get e to the power iota pi. Again, if you will write in this polar form, we'll get, now the angle is pi, right? So cos pi plus iota sine pi. Now what is cos pi? Cos pi is minus 1. Cos pi value is minus 1, and iota sine pi is 0. Sine pi is 0. So we'll get this answer as only minus 1. Answer we'll get is minus 1. Got it? Now next. Next we'll see the representation of complex number in vector form, right? So any complex number we can represent in vector form. Now, for example, if I write any complex number, suppose complex number z is there. Any complex number z is there. whose coordinate, whose complex number z is equals to x plus iota y. We can write that the coordinates of this z will be x comma y. So if we will join this complex number with origin, what will be the x component of this complex number? If I will drop the x, this x component length is x, right? And this y component is y. So this complex number z, I can assume it as vector, or the position vector of this complex number z, we can write as oz is nothing but x I cap plus y j cap. X I cap plus y j cap. Got it? So what will be our x, the component along x axis? The component along x axis will be equal to the real part of the complex number. Got it? And the component along the y axis will be equal to the imaginary part of the complex number. So any complex number we can represent in this vector form also. And what will be the magnitude of this vector, this position vector? The magnitude of this position vector OZ will be same as the modulus of complex number z. The modulus of the complex number z is what? Under root of x square plus y square. Got it? Now, so we can write here that any complex number can be represented in form of vector also, in the form of vector also. Got it? Now through questions we will see the more applications of this concept, this important concept, right? Now next we are going to discuss about the rotation theorem. Rotation theorem in complex number is very important. Got it? Now to see this rotation theorem, first we'll take two complex numbers. Let's suppose one complex number is z1 and the coordinates of z1 is x1 comma y1. Got it? And one more complex number is there, z2, and the coordinates of z2 complex number is x2 comma y2. Let's suppose the z1 vector makes a theta angle with x-axis and phi angle with, and this z2 makes phi angle with this vector z1. Got it? Or complex number z1. Now if we will write z1, in Euler's form, let's suppose the magnitude is same for both of them. Magnitude is r and r. I will discuss the cases when magnitude will be different also, but for now let's take the magnitude equal. So what I can write this one, this complex number z1, I can write as r e to the power I theta, right? And z2 I can write as r e to the power I, the angle z2 is making with x-axis is theta plus phi, right? So theta plus phi. Got it? Now next I'll try to simplify this one. If z2 again I can write as, it is r e to the power I theta multiplied by e to the power I phi. Got it? And what is this r e to the power I theta? We have seen here r e to the power I theta is nothing but r z1. Got it? So z2 here will be z1 multiplied by e to the power I phi. Now we can see that if in z1 complex number, if we'll multiply e to the power I theta, we'll get z2 complex number. Got it? Whose magnitude is same and who is making phi angle with z1, means the z1 vector, to rotate z1 vector, we have to multiply e to the power I phi, because I want to rotate this z1 vector with phi angle, right? What is the z2 vector? Z2 vector is nothing. Z2 vector is nothing but the z1 vector rotated with phi angle in anti-clockwise direction. Yes or no? So to rotate it, we'll multiply e to the power I phi. So e to the power I phi, this one we can write as, this is nothing but this is known as the rotation factor. So we'll write this one, e to the power I phi. It is a rotation factor which rotates any complex number by phi angle in anti-clockwise direction. Without changing its magnitude. Without changing its magnitude. So it will not change its magnitude, right? When we have to change magnitude, I'll discuss that case separately. Now, same, what if I have to rotate in anti-clockwise direction? We'll multiply with e to the power I phi, right? What if we have to rotate our complex number in clockwise direction? In that case, we'll multiply with e to the power minus iota phi. If we want to rotate our vector in clockwise direction, we will multiply with e to the power minus I phi, and if we want to rotate in anti-clockwise direction, we'll multiply with e to the power iota phi. So here we'll write, if we are multiplying e to the power minus iota phi, it rotates any complex number by phi angle in clockwise direction. In clockwise direction. Got it? So to rotate any complex number with the angle phi, we will multiply with the factor e to the power I phi. Actually, this was not possible in case of vectors, right? In case of vectors, the translation of vectors is possible. We used to move the vectors from one place to another place, but the rotation of vector was not possible, right? But in complex number, it is possible. If we will multiply with e to the power I phi, it is my complex number will be rotated. Got it? Now next, we'll see one example. Suppose, for example, I'll take two vectors. My y-axis. This one is my x-axis. Let's suppose here I have taken one vector or one complex number z1. Z1 complex number is 1, 0. Here I have taken one more complex number z2. Z2 complex number is 0, 1. The magnitude of both the complex number or modulus of both the complex number is same, right? This is my vector z1. The position vector of z1 will join with origin. So this is the position vector of z1, and this one is the position vector of z2. What is the angle between them? Angle between them is 90 degrees. Now, if I want to make z1 vector to z2 vector, if I want to make a z2 vector from z1 vector, so it was not possible in vectors, right? Because this is what this vector is I cap, and this vector is j cap, 1 j cap, right? This is separate vector and this is separate vector. In the vector chapter, there was no way to rotate this one I cap vector to make it 1 j cap vector. Got it? So, but in the case of complex number, it is possible. See, we'll try to make. See, from z1 we have to make z2 vector, right? So here, tell me the angle between both the vectors. The angle between both the vectors is 90 degree. 90 degree. From this z1 vector, if I want to make z2 vector, I have to rotate z1 vector by 90 degree in anti-clockwise direction. Got it? So z1 vector I'll multiply with rotating factor, which is e to the power I theta. And with what angle I want to rotate? With 90 degree I want to rotate. So e to the power iota pi by 2, I'll multiply to make z2. Now let's check what it is coming. See, z1 vector I can write as 1 plus 0 iota. Got it? And e to the power iota pi by 2 is cos pi by 2 plus iota sin pi by 2. Got it? Cos pi by 2 is 0, iota sin pi by 2 is 1 iota. Sin pi by 2 is 1, right? So here I can write this as 1 plus 0 iota multiplied by 0 plus 1 iota. So here if we multiply, so here we'll get 1 into iota. 1 into iota is iota. And iota is nothing but this complex number z2, right? By multiplying with e to the power iota pi by 2, we rotated our complex number with 90 degree. Got it? Now next, let's suppose they've given one complex number with magnitude r1. Right. So my y-axis, this one is x-axis. They gave one complex number z1 with r1 magnitude, and one more complex number z2 with r2 magnitude. The magnitude of this complex number is r1 and the name is z1. Now this complex number they're given z2 and the magnitude of this complex number is r2. Got it? Now the angle between both the complex numbers is phi. Now next, now what do we want? We want to make this z2 vector from z1 vector. Means I want to rotate z1 vector with the angle phi, and I want to change the magnitude also. Got it? So here we'll apply the concept which we used to apply in vectors, the unit vector. First we'll convert both the complex numbers as unit complex number or unit vectors. Got it? So we can write here z2 is nothing but z1 multiplied by e to the power iota phi. Now only it got rotated, its magnitude didn't got changed, right? So first we'll convert both of them into, we'll divide with their magnitude as we used to do in the vectors, right? Just like unit vector. Just like unit vector. So now this we can do, right? See, z1 upon z1 magnitude of z1 or modulus of z1 into e to the power I phi will give a unit vector along z2. Will give a unit vector along z2. Now when I'll send this modulus of z2 to that side, then the unit vector magnitude is 1, and modulus of z2, when it will get multiplied, it will make that unit vector with the r2 magnitude, right? Means this one I can write as z2 upon, what is the magnitude of z2? Magnitude of z2 is r2. z1, what is the magnitude of z1? Magnitude of z1 is r1, e to the power iota phi. Now I can send this r2 to that side, so I can write z2. I'll get, first I will rotate the unit vector of z1 with e to the power I phi, means with phi angle in anti-clockwise direction, and then this actually is giving direction, right? And multiplied by r2, this will give our complex number z2. So we have to remember this one. There is a relationship between two complex number with unequal modulus. Got it? Now next, suppose here we have taken the position vectors, right? Means we have taken the initial point as origin. Now let's suppose they have given something like this. They gave one vector, they have given another vector. This vector is z1, this vector is z2, and this time they are not originating from origin. This time they are originating from this. The initial point is this z0 vector, and I want to make z2 by rotating z1 with phi angle. Got it? In this case, what we'll do? See, just like vector will do. First, I'll write this vector. This vector I can write as z1 minus z0 vector. This vector I will rotate with e to the power iota phi. Means I will rotate with the angle phi in anti-clockwise direction to get the vector z2 minus z0. Got it? Now, if suppose their magnitudes are not equal, if magnitudes are equal, then this formula will apply. Otherwise, if magnitudes are not equal, again we'll make unit vector and we'll solve. Suppose I have taken this vector and I have taken one more this vector. Both vectors have different magnitude. This vector is z1, z0, z2. This is z1 minus z0 and z2 minus z0 does not have same magnitude. Got it? So in this case, but the angle between them is phi. So what we'll do? We'll make z2 minus z0 divided by modulus of z2 minus z0 will be equal to z1 minus z0 divided by modulus of z2 minus z0 multiplied by e to the power iota phi. Got it? So by doing this, we got a unit vector. We got a unit vector in the direction of z2 minus z0. Got it? Now, if we required whatever magnitude we require, that magnitude I'll multiply. So what is the magnitude of z2 minus z0? Is modulus of z2 minus z0, which if required will multiply. So this is the most general form of this rotation theorem. This is the most general form of this rotation theorem. Got it? Now next we'll solve some problems. After solving these problems, you'll get more clarity on this theorem. Suppose we'll solve this question. In this question they gave if ABC is an equilateral triangle. ABC is an equilateral triangle means all the side lengths are same. Then prove that z1 square plus z2 square plus z3 square is equals to z1 multiplied by z2 plus z2 multiplied by z3 plus z3 multiplied by z1. Got it? So first of all, here we will use the rotation theorem. See, I can write this vector. Got it? See, I can write this vector AB vector. What is AB vector? AB vector is this vector, which will be z2 minus z1. Got it? Position vector of B minus position vector of A. Now next we can write this CA vector or AC vector. What is AC vector? AC vector is position vector of C minus position vector of A. Got it? Now, can we tell the relationship between these two vectors, AB and AC? From AB we can get AC by rotating AB vector with the angle. What is the angle in equilateral triangle? All the angles in equilateral triangle is 60, 60, 60, right? So if we will rotate AB vector with 60 degree in anti-clockwise direction, I will get AC vector, right? The magnitude of both the vectors are same. As they said, it is an equilateral triangle, so side lengths will be same. Now, so we can write here that z3 minus z1 we can get by rotating z2 minus z1 vector with e to the power iota phi by 3. We'll multiply with e to the power iota pi by 3 to rotate it in anti-clockwise direction with angle 60 degree. Now next I can see this vector. We'll see this vector. This vector, suppose this vector is BC vector. This BC vector will be position vector of C, which is Z3 minus Z2. Got it. And one more vector I'll take is this vector I'll take. AB vector. This complete AB vector I'll take. This complete AB vector. So AB vector will be, or BA vector. Sorry, BA vector will take. So BA vector will be position vector of A, which is Z1, minus position vector of B, which is Z2. Got it. Now we can write that this from this BA vector, we can get this BC vector. We can get this BC vector by rotating it in anti-clockwise direction. Sorry, by rotating it in clockwise direction. Or instead of rotating it in clockwise direction, from this BC vector I'll get AB vector by rotating it in anti-clockwise direction. So here we can write here that Z1 minus Z2 vector, which is my BA vector, I can get by rotating BC vector, which is Z3 minus Z2 in anti-clockwise direction with 60 degree. Understood? This is my equation number 1. This one is my equation number 2. Now we will divide both the equations. We will divide both the equations. So what we'll get? So here we'll get Z3 minus Z1 divided by Z1 minus Z2. On this side, in right hand side, we will get Z2 minus Z1 divided by Z3 minus Z2. And here the rotating factor is e to the power iota pi by 3. Here also e to the power iota pi by 3. So this e to the power iota pi by 3 and e to the power iota pi by 3 will get cancelled. Now we'll cross multiply. So after cross multiplying, we will get here Z3 minus Z1 multiplied by Z3 minus Z2 is equals to Z2 minus Z1 multiplied by Z1 minus Z2. Now open the brackets by multiplying. So here we'll get Z3 multiplied by Z3 is Z3 square. Z3 multiplied by Z2 is minus Z2 Z3. Z1 multiplied by Z3 is minus Z1 Z3. Next, Z1 multiplied by Z2 is minus Z1 Z2. And this side will get Z1 into Z2. Sorry, Z2 into Z1, which is Z1 Z2. Next again, Z2 multiplied by Z2 is minus Z2 square. Z1 multiplied by Z1 is minus Z1 square. And minus Z1 multiplied by minus Z2 is plus Z1 Z2. Got it. Now from here, we can see that from here we can see that here we get plus Z1 Z2, right? Minus Z1 multiplied by minus Z2 is plus Z1 Z2. Now plus Z1 Z2 and 1 plus Z1 Z2 got cancelled. Now this Z2 square and Z1 square I'll send to that side. So here I'll get Z1 square plus Z1 square plus Z2 square. Here I'm having Z3 square, so plus Z3 square is equals to the Z2 Z3 I'll send to that side. Z1 Z3 also I'll send to that side. So here I'll get Z1 Z2, which is already there, and this I'll send to that side. So plus Z1 Z3 plus Z2 Z3. This is what they said in question to prove, right? So hence proved. Now in this question they have given a right isosceles triangle. and they gave equation z1² plus lambda z2² plus z3² is equals to lambda times z2 and multiplied by z1 plus z3. Find the value of lambda, they said. Got it? So this is a right isosceles triangle, so we can say that this line z1 minus z2 and this line z3 minus z2 have same magnitude. Got it? Or we can say that if we will rotate this line z1 minus z2, if we will rotate with pi by 2 angle in anti-clockwise direction, with iota pi by 2, to rotate I'll multiply with the rotating factor e to the power iota pi by 2. I'll get the vector z3 minus z2. Got it? Now one more thing. These are the important things you have to remember, that e to the power iota pi by 2, this will be equal to cos pi by 2 plus iota sine pi by 2, right? Cos pi by 2 is 0, iota sine pi by 2 is iota into 1, which is 1. So this will give iota. So e to the power iota pi by 2 will always be equal to iota. Now if they have e to the power iota into 0 radian, so this will be cos 0 plus iota sine 0, right? Cos 0 is 1, iota sine 0 is 0. So here I'll get this is 1. So e to the power iota 0 is 1. Next, if I'll say what is e to the power iota pi, so this will be cos pi plus iota sine pi, right? Cos pi is 0 and sine pi is, cos pi is minus 1 and sine pi is 0, right? So here we'll get this as minus 1. So e to the power iota pi will be equal to minus 1. This we have to remember. Now next, here I got e to the power iota pi by 2. Just now I proved that e to the power iota pi by 2 is equals to iota. So this one is nothing but iota. So here we got z1 minus z2 multiplied by iota is equals to z3 minus z2. Now do one thing, do squaring both sides. So we'll do squaring both sides. So we'll get here is z1 minus z2 square multiplied by iota square is equals to z3 minus z2 square. Got it? So from here we'll get z1 square plus z2 square plus minus 2 z1 z2, and this iota square is minus 1 is equals to, here we'll get z3 square plus z2 square minus 2 z3 into z2. Got it? After multiplying with minus sign, I'll get a minus z1 square. Sorry. So here we'll get, after multiplying this minus sign inside, we'll get a minus z1 square minus z2 square plus 2z1 z2 is equals to z3 square plus z2 square minus 2z3 z2. Got it? Now all the things I'll bring to one side. So this z1 and z2 I'll take to that side, and this minus 2 z3 z2 I'll bring to this side. So here I'll get 2 z1 z2, and when I'll bring this to that side I'll get plus 2 z3 z2, and remaining everything I'll send to that side. I'll get here z1 square minus z2 square, and z2 square is 2 z2 square. Got it? Plus z3 square. So if we compare this equation, or I can take here 2, first I'll take 2 z2 common, right? So here I'll get 2 z2 and z2 plus z3 is equals to z1 square plus 2z2 square plus z3 square. Got it? Now next, if we compare this with the question, we'll get that lambda value is 2, right? They're asking the coefficient of lambda z2 square, coefficient of z2 square. So coefficient of z2 square is 2. So our lambda value in the question is 2. So lambda value is 2. This is our answer. Got it? Thank you.